You're building an e-commerce checkout for the last PlayStation 6 in existence. Suddenly, 3 users click buy at the exact same millisecond. Welcome to the read, modify, write race condition, the silent killer of data integrity. In a perfect world, requests happen one by one. But in reality, all 3 query the database. All 3 see stock equals 1, and all 3 decide it's safe to decrement. They all write 0 back to the disk. The application says success. But your inventory manager is about to have a very long night explaining why you sold 3 consoles when you only had 1. This isn't just a bug, it's a fundamental failure of state management. Time to lock it down. Meet pessimistic locking, the trust nobody approach to database safety. Think of it as a cynical bodyguard for your data. User A starts a transaction and slaps an exclusive lock on that row using select for update. User B tries to read, blocked. User C tries to write, also blocked. They wait in line like good citizens until the transaction commits and the lock is released. It's safe, but it's slow. If user A gets stuck calling a slow external API or hits a network hiccup, your entire system grinds to a halt. Connection pools explode, memory spikes, and your users start hitting the refresh button in frustration. You traded performance for absolute safety. Hope it was worth the 100% CPU usage. But pessimistic locking has a final boss, the deadlock. Imagine transaction 1 locks row X and needs row Y. Meanwhile, transaction 2 locks row Y and needs row X. They're stuck forever in a toxic digital stalemate, each waiting for a resource the other holds. It's like a 4-way stop where everyone is waiting for someone else to go. The database engine eventually realizes the circular dependency, plays God, and kills one transaction to save the system. The victim gets an exception, and you're left to pick up the pieces. To avoid this, you'll need shorter transactions, lock timeouts, or sophisticated retry logic, because even with consistent ordering, complex race conditions are always lurking. Optimistic locking enters the chat, the trust but verify strategist. It assumes conflicts are rare, so it doesn't block anybody during the read phase. Instead, we add a version column or a timestamp to the schema. Everyone reads the same data. Stock equals 1, version equals 1. But when it's time to write, the database performs a compare and swap operation. SQL says, update to 0 only if the version is still 1. User A arrives first, matches the version, and succeeds, bumping the version to 2. User B arrives milliseconds later, sees a version mismatch, and the update fails silently. No wasted memory. No blocked threads. Just a clean rejection. Move along. But optimistic locking shifts the burden of conflict resolution from the database to your application. If an update fails, you just retry, right? Simple. Now imagine a big flash sale with 1,000 users, all retrying at the exact same time. Welcome to the retry storm, where your database CPU hits 100% just processing endless validation failures. You've effectively DDoSed yourself. The fix? Exponential backoff with jitter. Force your application to wait and randomize that delay so the retries are spread out like a beautiful staggered wave. It gives your database room to breathe and actually complete some work instead of just telling people no. Scaled to microservices? Row-level database locks won't save you when your data is sharded across the globe. Enter distributed locking. Redis to the rescue. Instead of locking a row, we create a global lock in a fast central store like Redis, with a key like lock product 123. We use the red lock algorithm for high availability across multiple nodes, ensuring that a single failing Redis instance doesn't break our consensus. But never forget the most critical rule. Always set a TTL. If your application crashes while holding a lock without a time to live, that resource is deadlocked forever until someone manually intervenes. Life is dangerous in the cloud. Before you over-engineer a complex distributed system, stop and ask yourself, do I really need a lock at all? For simple math and state changes, use native atomic operations. One SQL statement handles the read, modify, and write cycle in a single, uninterruptible step. Update products set stock equals stock minus 1, where ID equals 123 and stock greater than 0. The database engine handles this at the hardware level, using CPU mutexes with extreme concurrency. It's microseconds instead of milliseconds. No application logic, no network hops, no race conditions. Sometimes the most elegant solution is the one you don't even have to write. Recap. Pessimistic is your heavy tank, unstoppable but slow. Optimistic is your agile assassin, fast until it gets spotted. Distributed is your orbital strike, global impact with high coordination costs. And atomic? That's just clean, surgical math. Your architectural choices define your system's survival. Pick the right lock, keep your data pure. And remember, at scale, every millisecond counts. Code with confidence, and stay synchronized.